So this is the first lecture video on the gas laws. And in the gas laws, no matter which portion of the gas laws we're going to be talking about, the most important equation is the ideal gas equation. This is the equation where we can derive all of the laws in terms and obviously mathematical equations for the gas laws. Very, very important. Most important equation. All right. So I'm going to talk about relationships first. So we have what we call direct or inverse relationships between variables if they are on the same side of the fraction bar. So the fraction bar is this bar that separates the numerators from the denominators. Okay, if they are on the same side of the fraction bar, so pressure and volume is on the same side of the fraction bar, or number of moles and temperature is also on the same side of the fraction bar, albeit pressure and volume is in the numerator together and moles and temperature is in the denominator together. They have an inverse relationship. Inverse relationship means that if the pressure increases, the volume decreases, and vice versa. Okay, so if the pressure decreases, the volume has to increase. So that's called an inverse relationship. It's called an inverse relationship because they go opposite ways. One goes up, the other goes down, and vice versa. Okay, and that would be the same relationship between the number of moles, which is N, and temperature. If the number of moles increases, the temperature also increases, in this case for gases again. All right. And as we're going to be going through the gas laws, we're also going to be talking about kinetic molecular theory, and this is going to hopefully explain more of this phenomenon better to you. So that's inverse relationship. Now, if they're on opposite sides of the fraction bar, like pressure and the number of moles pressure is in the numerator, number of moles is in the denominator, we have what we call a direct relationship. Direct relationship means that if the pressure increases, the number of moles had to increase as well. Okay, that means to say that there's also a direct relationship between volume and temperature, right? So if I increase the temperature, if everything else is held constant, that means to say that the volume will also increase, right? Very, very important. Okay, so we're going to be talking about that. The units of pressure and volume, obviously, N is moles. So moles is R is the gas constant. This is the gas constant, 0.0821. Embedded with multiple units. It's actually 4 units, liters times atmosphere divided by moles times Kelvin. The only absolute, so anytime you use R, the units that you have to use are these units: liters, atmosphere, moles, and Kelvin. There is a way that you can use other units, but you need to have a derivation of this number beforehand, which is a much more complex, which we don't need to do in this class. Okay. So, however, here's an absolute rule, okay, and that's actually quite funny because it's called absolute. You always need to use absolute temperature, and absolute temperature means you have to have the temperature always, regardless of what mathematical equation you're using. If temperature is in play, the unit for temperature always has to be in Kelvin. And the conversions for Kelvin is actually in your unit conversions portion of your exam reference sheet. Okay, so very, very important. Again, I hope that you understand direct and inverse relationships, and we're going to be going on with the gas laws right away. Right, so, and this is covering thing. So the first law that we're going to be talking about is Boyle's law, which is about pressure and volume, and this is a sample mathematical problem. It says, what is the new pressure when a gas that was in a 15-liter container, so that's obviously volume, with an initial pressure initial pressure means initial P1, okay, of 3.2 atmospheres, was compressed to 2 liters. Now you have 2 volumes. Now very, very important is before any problem begins is you need to figure out what is P1, what is P2, what is V1, what is V2. From, when you hear the word from, that's always initial, it's always 1. P1, V1, N1, whatever that would be, okay? When you see the word 2, like 2, TO, that means it's the second unit, like that means P2, V2, whatever that would be, okay? So in terms of the 2 units for volume, this would be the initial volume, and this would be, or P1, and this would be P2. I'm sorry. Did I say P? I meant volume, okay? This is V1, all right? And this is V2. And this is obviously initial pressure. That means initial. This is pressure 1. All right, so if we do the math, and again, the way that you would figure out which formula to use is you go back to the ideal gas equation, the way it was written in the previous slide. Just to give you an FYI, like this. All right, and what you do is you eliminate units that do not appear in the problem. Okay, so obviously there's units for volume, so volume has to appear. There's no moles. There's no gas constant, there's no temperature, so all of those units that is not included gets eliminated, okay? And the question is, what's the new pressure? So pressure is the question, so obviously you need to have both P1 and P2, right? So now you have simplified, the ideal gas equation is now P1V1 equals P2V2, right? And that's actually called Boyle's law. And so you would just plug into the equation all the numbers. Okay, so pressure 1 is 3.2 atm, volume 1 is 15 liters, P2 is the unknown, and 2 liters is the new volume, okay, because it's after the word 2. You do the math, so you do 3.2 times 15 divided by 2, right? So again, this is multiplication. The inverse operation of multiplication is division, and I hope that you kind of know your math. This is a prerequisite for this class anyway, so again, 3.2 times 15 divided by 2. And if you do the math, the actual new pressure is 24 atmospheres. Okay? Now, again, remember that these variables are on the same side of the fraction bar. Okay, so they're both numerators. So it should make sense that if I decrease the volume, I want you guys to compare the volume, the initial volume, with the second volume. What happened to the volume? The volume decreased. And since they are on the same side of the fraction bar, remember that they have what we call an inverse relationship, okay? So if I decrease the volume, the pressure had to increase. So the pressure, the new pressure, had to be greater than the initial pressure. If you had an answer of less than the initial pressure and the volume has decreased, you made a problem already. Okay, so you already have a bigger problem than initially was presented to you. So again, it should make sense. You need to always look at your numbers. Okay, so again, if I decrease the volume, the pressure had to be greater than 3.2 atmospheres. If I increase the volume, if the volume of this, if this V2 was bigger than the 15 liters, then what we need to assume is the new pressure would be smaller than 3.2 atm. Okay, and again, that is called volume is decreased, pressure is increased, and vice versa. And this is called an inverse relationship. Okay, and again, the reason why is because the variables P and V are both in the numerator, or they are both in the same side of the fraction bar. Okay, very, very important. So another sample problem, what is the new volume? So this time we're going to be asking for a new volume. New volume means we're looking for V2. Okay, when a gas that has an initial pressure means P1, 5.6 psi. Initial volume means V1, right? Initial volume of 78 ounce has a new pressure of 1.7 atm. So this is a P2 in this case. So we're looking for V2 again. Now the problem is, if I plug this in, your units of pressure, your units of volume, or whatever two units have to be given to you have to be the same unit. So we need to do a little bit of conversion initially. So it's your choice, but for me, I'm changing PSI to ATM. And according to your unit conversion sheets in your gas law page, actually, there are, you have to do dimensional analysis again. So 5.6 PSI times 1 ATM divided by 14.7 PSI. Recall that in dimensional analysis, the given unit has to be in the denominator in the ratio that's given to you. And that's actually how you cancel units. And 5.6 ATM and PSI. Now here's the deal. I kind of forget to mention before, significant figures. The given unit is 2 significant figures. Your answer has to be in 2 significant figures as well. Same here. In this calculation in the previous problem, you had 3 significant figures. This 0 is significant because there's a decimal point. two significant figures, two significant figures. Again, this 0 is significant because there's a decimal point. So the answer had to be in two significant figures. Okay. But going back to this problem, so the first thing we did was we converted PSI into ATM. Then we plug it into this equation again. Okay, P1V1 equals P2V2 again. This is pressure 1. So this is pressure 1 now. So PSI has now changed into ATM. The initial volume is 78 ounce. And the new pressure is 1.7 ATM. So P2 is 1.7 ATM. All right. We do the math. Okay, 0.38 ATM times 78 divided by 1.7. Now here's the deal. You need to do a little bit of prediction again. What has happened to the pressure? The pressure went from 0.38 atmospheres to 1.7 ATM. So the pressure in this case increased. We need to understand that since this is an inverse relationship, that the volume had to decrease. So the answer, the number that we need to get, has to be smaller than 78 ounce. And lo and behold, that is the case. The new volume is 17 ounce, which is smaller than the initial volume. Again, because this is a inverse relationship. Okay, very, very important. Good. So that's Boyle's law, ladies and gentlemen. So the next law, we're just gonna keep chugging along. I hope you make sure that you pause this video, do some problems, okay, especially your homework problems, and keep going. Right. So next law, Charles' law. So the Charles' law is the relationship between volume and temperature. Okay. And you know what? I already forgot. I actually need to talk about kinetic molecular theory about Boyle's law. Okay. Why is there an inverse relationship between pressure and volume? Okay, I'm very, very sorry. I'm jumping all over the place here, but we're just going to go back here. And the reason why this is you have to understand. So if I have, okay, let's say 3 gas particles in this container, right? What they're doing according to kinetic molecular theory is they're going to be bouncing off the container and bouncing off each other. Right? So that is actually the pressure in containers, are actually the pressure, in this case, the force exerted by highly, in this case, fast-moving gas particles against the walls of the container. So that's pressure. Now, what happens if I make the volume smaller? And these 3 particles have the same kinetic energy as previously. Well, before, because they have a bigger volume, the amount of time and the frequency in which they collide with the walls of the container is less. Right? If I make the walls, the container, smaller, now they will more frequently interact. They will frequently bounce off each other and bounce off the walls of the container more. That is why their pressure, when you make the volume smaller, increases. Okay? So again, this is dependent upon the kinetic molecular theory. Again, so again, think about yourself, right? So if you put, okay, and this is a terrible analogy here, if I put someone who has ADD in a 500 by 500, you know, like, I don't know, 50,000 square foot room, there'll be obvious, you know, like obviously people have ADD or whatever, we term them bouncing off the walls, right? That's a gas particle. The frequency in which they're going to interact with the walls is going to be less. Now, if I put the same person who has ADD, who's like spaz, who, you know, besides adult, like ADD, also has now taken a sniff of, you know, like of medication that actually in this case makes them more hyperactive. What happens is, if I put them in a smaller room, now they're going to interact with the wall more. Okay, so that's pressure and volume relationship. I hope that makes sense.